Hello, everyone. I'm Yankee. I'm a statistics PhD at Harvard and also an intern here at the Toronto AI Lab. I'm going to introduce multi-student diffusion distillation, joint work with James and John from our group, as well as Wei and Karsten from the conditional generative AI group. Some quick motivation. One of the important next step for nowadays generative AI research is speed, because we already have very high quality generative AI models, but to enable real-time applications such as holodeck, DLSS, generative games, and interactive LLMs, we really need to accelerate these models. Specifically, if we look at diffusion models, which are the backbone of many SOTA generative AI models, they often require a very long iterative denoising process, which can take as many as 50 steps from this visualization. And B, they also require a very large model as a single step forward model, and it can be quite slow and memory intensive. For example, these SOTA image generation models can take several seconds to generate a high quality image. For video models, it can take as much as a couple minutes or like tens of minutes. And they usually take as much as 20 gigabytes of memory, which prevents it from working on like customer grade GPUs. There has been many work on diffusion acceleration, and in this talk, I'm going to focus on the last part, which is knowledge distillation. It treats diffusion model as a teacher and tries to train a student generator that generate the teacher quality with like much less steps. Consistency models is one more famous class of diffusion distillation models, but the state-of-the-art method are now actually using distribution matching and adversarial distillation techniques, which is the techniques that we're going to use in our experiments. So we talk about acceleration, we need to ask the question of how fast is fast enough, right? Like I mentioned, for real-time high-quality video generation, it can take tens of minutes. So in order to really make it real-time, we not only need to try to reduce the denoising step to as few as a single step, but also want to use smaller architecture for that single step in order to actually generate a 5-second video within 5 seconds. So we need these two types of model reduction, which means that the model capacity is definitely going to decrease, which leads to decreased performance. So this is kind of dilemma here. And we want to know how to actually maintain a large model capacity with faster generation time. And this is why we're proposing our method. And now I'm going to formally introduce our method, multi-student diffusion distillation. In one word, we propose to distill a teacher diffusion model into many smaller and also single-step student generators. Each student works like a specialized expert that focuses on data subsets. At inference time, given a new user request, we route the request to retrieve the specialized student and only use that student for generation. If we think about all those students collectively, they have larger model capacity, so hopefully better performance. But at the same time, since only one student is used, this leads to decreased latency. So we kind of have a win-win situation here. I mentioned we need a routing strategy to retrieve different students, and I'm going to propose a couple of methods of how do we use the routing or like partitioning of the set data into different students. A simple method is manual partitioning. This works especially for discrete class conditioned generation, such as image generation in CIFAR10 and image in NAT64. We can usually find semantically meaningful clusters in sequential of those labels, and we can just assign different partitions into it. A more general strategy is embedding space clustering. If we look at a lot of diffusion models, they usually have this encoder layer where they encode the condition, which can include text, semantic maps, and images into the embedding space. Since these are just vectors in the embedding space, we can use different clustering methods like k-means clustering to get different partitions and assign into different students. We obviously have like different specialized strategy for different applications. For example, for autonomous driving, we can assign different cities to different students. For games, we can assign different types of games to different students for applications like DLSS. So we now have a routing strategy for student at inference. At training, we do something very similar. We now not only route different prompts or like class conditions, but also route corresponding training data into different students. And we do different student training in parallel, which means that we will not incur longer training time. To summarize what we have now, we now propose a framework to distill a single teacher into multiple single-step students. We use the state-of-the-art distillation techniques that includes distribution matching and adversarial distillation. I'm not going to go into details here. I need to emphasize that for these two methods and almost all other distillation methods, they need to use the same architecture for teacher and student. And this is what we have now. We do this on a very simple toy model, and we see that the more student we used, the better performance we're going to get. However, we're not done. Like I mentioned, in order to achieve like real-time generation for things like video, we not only need to reduce to a single step, but also want to make the architecture smaller. So I said that currently almost all distillation techniques need to use the same architecture, and this is because they need to initialize the students with teacher weights. And this turns out to be actually very important. If we look at a small ablation study, we find that if we initialize the student randomly, then it performs quite a bit worse as the student initializes the weights from the teacher. And this is a problem for smaller architectures because for smaller students, we cannot initialize the teacher weights. We propose to mitigate this issue by introducing another stage called teacher score matching stage. Basically, we distill into a smaller multi-step diffusion model student first by matching the student scores with the teacher scores. Then we follow with the step distillation. This additional stage helps the student with learning good feature maps and initialization weights, which can be very helpful for the later single-step distillation stage. A short summary. In order to distill into a smaller student, we need to apply three techniques. We first do teacher score matching to distill into a multi-step student and make it smaller, then followed by single-step distillation using distribution matching and adversarial distillation techniques. So we apply all the techniques we have into some experiments. Here we distill a Stable Diffusion 1.5 teacher into a single-step student with the same architecture as well as with smaller architecture. We see that for single-step same architecture student, the generation quality almost match with the teacher. And with a much smaller student that specializing on dog-related subsets, we see that we still have very good generation quality, and now with a much smaller architecture. On a more quantitative side, we compare one student with 4 students in many different situations, for example, in class conditional and text conditional generation, and also with different distillation techniques. And we find out that in all of these cases, 4 students has better performance than 1 student. This shows that the multi-student distillation framework is very robust. A quick summary, we present multi-student distillation, which is a framework that distills into specialized students, each focusing on a subset of the data. This leads to more students and therefore better capacity with smaller student size and therefore better latency. We can control the number of students as well as the student size according to our training resource as well as business needs. This framework is very general in the sense that it should work with different distillation methods, and we actually confirm this by trying, for example, consistency distillation. And this framework is also very compatible with many other acceleration techniques, such as pruning, which which helps finding smaller students smarter.